This is the fourth talk. Okay, it's about time for 10 a.m. and also 9 p.m. in United States. I think 9 p.m. due to this is a daytime saving time. So they changed the time from March 14th. So this is the fourth talk in this seminar series, present series. So we would like to try to promote people to understand how the satellite data to improve, such like weather or climate study and environmental. So today we are talking about a typhoon. And then we're glad to have Tim Olander to share his current research about how to derive the typhoon intensity from satellite observation. I think he will online sometime he is convenient because he already sent us a pre-recorded video clip. And he said he will online at his convenience. Probably already on, but I'm not sure. So let me give some of the introduction about him. Tim Olander, he is a researcher at CIMSS, Wisconsin. CIMSS stands for Cooperative Institute for Satellite Meteorology Study. So that's one of the largest meteorology satellite study center in the United States for a very long historical history. I think more than 50 years. And the location is in the University of Wisconsin. And Tim Olander is a researcher over there, and he is primarily associated with advanced the technique. If you are working on typhoon intensity estimation, this is very useful tool and number to estimate the typhoon intensity. And he is a primary algorithm developer, so he will know everything, all the detail about how to derive that. And also, he is a PI for GOES-R. That's what we heard on the first talk. Now it's GOES 16 and 17. He is a PI for GOES-R hurricane intensity estimation algorithm. So he's working on both, not only the intensity from satellite observation to detect typhoon intensity, but also for GOES-R observation. And he also maintained the tropical cyclone webpage. So if you click the CIMSS website, you will see the typhoon webpage. He is a maintainer. So if you want to work on algorithm, you also provide the data. And previously, he working on atmospheric motion winds, which means they can derive the wind factor in different altitude from satellite observation, and also working on AMSU, Advanced Microwave Sounding Unit Retrieval, and also from hyperspectral interferometer sounder to guide the student over there. I'm not sure he's here on the time online or not, but well, his talk lasts for about, let's say, 40 minutes. So let's start for the talk of the day.
Hi, good morning. My name is Tim Olander, and I'm a tropical cyclone researcher at the University of Wisconsin-Madison CIMSS. And I've been working at CIMSS for about 26 years in the field of tropical cyclone meteorology and analysis using satellite imagery. And today I would like to talk to you a little bit about some of the products being developed at CIMSS. There are three main points to my talk today. The first will be the advanced Dvorak technique, something I've been working on for many years. The second will be the satellite consensus algorithm, or SATCON. And the third is a new routine we are developing to augment the ADT using machine learning. So here's the first topic, will be the ADT. The ADT, again, was developed by myself and Chris Veldon. And we've been, like I said, working on this for almost 20 years. So what is the ADT? The ADT has been in development since the late 1990s in order to remove much of the inherent subjectivity from the operational Dvorak technique. The operational Dvorak technique has been used around the world since the late 1970s when it was developed by NOAA scientist Vern Dvorak. The technique is shown in the bottom left corner, which is a top-down technique, which first identifies the storm scene type, which is like an I or CDO shear curve band. Those are the main scene types. And then from there, it applies various rules to limit its intensity changes over time, and other rules are employed to provide a final intensity estimate analysis. The reason we did the ADT was to try to remove some of the inherent subjectivity of the Dvorak technique. On the graph provided on the bottom right, you can see a intensity analysis for Hurricane Iris, which was in 1995. The best track is in black, and you can see various intensity estimates provided by the Dvorak technique, provided by the various symbols. And in certain situations, you can see there's a variation of up to about 30 hectopascals in some regions of the storm. And this type of subjectivity is what we were trying to eliminate with the development of the ADT. The ADT is used operationally around the world at such forecast centers as the National Hurricane Center in Miami, Florida, and the Joint Typhoon Warning Center in Pearl Harbor, Hawaii. In addition, it is also used at other tropical cyclone forecast centers around the world, such as those in Australia, India, and Japan. It has also been used in several climatological studies, two of which are done by my colleague Jim Cosson of NOAA and are listed at the bottom left corner. The 2020 study received a great deal of coverage by various news outlets in press and on the internet. Listed here are the main upgrades of the current version of the ADT, version 9.0. I won't go into any major details about any of these upgrades, because it would take too long, but if you would like more information about these upgrades, I will provide a citation for our latest ADT paper later on in this talk. Here's a general overview of the ADT processing. The Archer technique, which I won't describe here, was developed at the University of Wisconsin by my colleague Tony Wimmers, provides the ADT with a first guess position objectively determined using various satellite imagery. Once the position is provided to the ADT will then determine the scene type objectively, and from then it will determine the intensity of the storm using various processing techniques within the algorithm itself. The output will then consist of various graphical and text outputs to display various parameters used in the technique to the tropical cyclone forecaster, who can then use this as an estimate to determine the tropical cyclone intensity. Some of the scene types that I just mentioned. Here are some examples of the different scene types. There are some eye scene types on the left and some cloud scene types on the right. Once the intensity is determined from this scene type, that is known as the raw T number, which is basically a first guess. Various Dvorak technique constraint rules limiting the amount that the tropical cyclone can increase or decrease over time are then applied along with a 3-hour time-weighted averaging scheme, and this will provide the final T number. From there, an additional set of weakening rules are applied to the values over time based upon the Dvorak technique, and this is outputs what's known as the current intensity or CI number. As I mentioned, there are various techniques in the ADT to derive the intensity estimate. For certain scene types, like the eye scenes and certain cloud scenes, like the CDO scenes, which the CDO is a central dense overcast, when there is a cirrus shield obscuring the eye forming underneath the cloud shield. We use regression equations to derive these intensity estimates. These are based upon various parameters, such as the size of the CDO, the cloud top temperature, or the eye temperature. Some of those are some various parameters that go into the derivation of the regression equation. Other things like the curve band or shear scene type, we utilize various techniques provided in the original Dvorak technique to provide the initial intensity estimate. Here are some 2019 performance statistics for the West Pacific, North Atlantic, and East Pacific during the 2019 tropical cyclone seasons. The East and West Pacific estimates are validated against best track from either NHC or JTWC, while the Atlantic are validated against best track that are within plus or minus 3 hours of aircraft reconnaissance. As you can see, the West and East Pacific have a fairly Gaussian shape, while the Atlantic has a little bit of a tail of an underestimate bias, which shows up in the bias statistics for the North Atlantic. And this, we believe, is due to some new instruments being utilized by NHC in their derivation of the best track, one of which is called the Step Frequency Microwave Radiometer, SFMR. And this might be giving new information to the forecasters that are showing up in their derivation of the best track estimates, which obviously the ADT has not accounted for in the regression equation derivation. So we're looking into this and see if this is causing some of the new biases we have been noting in the last couple of years. But again, the standard deviations of errors here in the various parameters are pretty good overall. For the West Pacific, we're getting a bias of around 11 knots. In the East Pacific, just under 10, while the North Atlantic was around 13.5 for the wind speeds. Here's a couple of examples for the 2019 cases. These are for the West Pacific, and you can see again how well the ADT in the red line compares to the best track estimates, which are shown in the blue line. The various symbols are the operational Dvorak estimates for these different storms at 6 hour, typically they're done at 6 hour intervals. And you can see there's quite a bit of variation in some of these estimates during even the most intense parts of the storm. And this, again, is why we were trying to develop the ADT, was to eliminate some of these biases and subjectivity from the various Dvorak analysis at these different operational centers. Here are some more examples, and again, I'm trying to highlight some of the spread you can see in various parts of the different storms, whether it's at the most intense parts of the storm or during some of the weakening phases. And again, the ADT is just another tool that the forecaster can use to help derive the intensity estimate. In the last example, this is a good case of where the ADT in the Atlantic had a bias, an underestimate bias compared to the best track. And again, this might be because instruments such as the SFMR were used in the derivation of the best track, and the ADT will probably need to be rederived to use some of these new instruments, although there are some questions about how accurate the SFMR is at higher intensities. So we are still examining these. Here's a nice case of Hurricane Patricia during the 2015 East Pacific tropical cyclone season. The ADT estimate is shown in the blue line, with aircraft reconnaissance measurements shown in the purple dots. And you can definitely see the strong similarity between the ADT and the actual recon measurements. So this was a very good case for the ADT, showing how accurate it can be in certain cases. Finally, here are some noted publications. In the top left, you can see our latest ADT paper that was published in 2019. Below that are some cases from various operational center, such as Australian Bureau of Meteorology and ECWF use the ADT to do some various research efforts. And then the bottom one was one performed by myself and Chris Veldon. We reprocessed some of the top tropical cyclone cases during the satellite era around the globe and re-ranked them using the ADT. So where can you find the ADT? Well, you can find it on our Tropical Cyclone webpage, and here's the address. Again, these are provided for all storms globally around the world in real time. So you can go to this page and take a look at the ADT performance at any time you wish. The next portion of my talk will consist of a discussion of the Satellite Consensus Algorithm, or SATCON. SATCON was developed at CIMSS by two colleagues of mine, Derek Herndon and Chris Veldon, and has been in development for many years. Okay. Many different satellite-based tropical cyclone intensity estimation algorithms are available, including those that use either geostationary and polar orbiting imagery. Some are listed here. The ADTs we already discussed. The cloud method developed at JMA. Various scatterometers look at sea surface winds. Microwave sounder methods. The deviation angle variance technique, and SMAP radiometers. To account for the different tropical cyclone storm structures, it's best to use different algorithms and know the strengths and weaknesses of each one. This is what SATCON does. It can combine the best attributes of different algorithms and provide the best estimate available. For geostationary, you can look at intensity, position, and structure elements. Microwave imager, you can look at position and structure. And then microwave sounders, it can look at intensity and structure algorithms that derive intensity estimates. The SATCON uses many different types of sensors in the derivation of its intensity estimates. It uses three available passive microwave sounders, the ATMS, the SSMIS, and the AMSU. Different channels are used for each different sounder. For the ATMS, CIMSS and CIRA, which is the Cooperative Institute for Research in the Atmosphere in Fort Collins, Colorado, they each use a different algorithm utilizing different channels from the ATMS. Since the microwave imagery is not available at the frequency of geostationary satellites, the ADT is also used in the SATCON. We won't go into a lot of detail about this, obviously, because we just talked about the ADT. One point to make, though, is that the IR imagery used by the ADT only looks at the cloud tops, which has its limitations, especially in situations like I've discussed previously when there's a CDO structure over the storm center obscuring the eye forming underneath. Microwave sounders can look underneath the CDO structure and look at the warm core structure of the tropical cyclone at various levels in the atmosphere. This is a cross-section of a storm, looking at the various weighting functions at various channels for, in this example, for the ATMS. You can see the different channels from channel 7 to 10 work upwards in the atmosphere at different levels, looking at the warm core structure at these different levels. And we can use these observations to infer tropical cyclone intensity. Looking at the different microwave sounders that are being used, you can see they have different resolutions, anywhere from 32 kilometers for the temperature sounders, up to 48 for the AMSU, or for the moisture and imager resolution, they can go from anywhere between 12 and 16 kilometers at nadir. But it's much higher as you look out at the limbs, since these are cross-track type scanners. Okay, so here is a general overview of how intensity estimates are derived using the microwave sounder techniques. This one for the one derived at CIMSS. Okay, so first, a center position is determined either by using the forecast interpolation or the use of Archer, which I described in the ADT. The warmest pixel is then identified and a filter is applied to the image to smooth out some of the noise and reduce some of the noise, or take out some unrepresentative temperatures that might be in the image. Okay, a temperature anomaly is then derived between the warmest center pixel, here shown in where the arrow is, and a surrounding ring, which is about 5-degree radius from that center position. This is repeated for the 4 different channels that I showed you before at different heights in the atmosphere. Regression equations for each channel are used to estimate the pressure anomalies based upon this temperature signature, and the eye size estimate can adjust these values if there is an eye. Okay. Finally, the estimate for maximum wind speed value is based upon the pressure anomaly and other parameters that go into this regression equation. So why do we do SATCON? Well, it's beneficial to objectively and skillfully combine the 4 different algorithms in the SATCON ensemble in order to save the forecaster's time. That's the primary impetus behind the SATCON, is to save the forecaster's time. Instead of having to look at 4 different estimates, they can just look at one. So the 4 different methods that are used in the SATCON are the ADT, as I mentioned before, the CIMSS-AMSU, the CIRA-AMSU method, and the Archer, although the Archer is only used to help provide center location and the eye wall size and convective vigor to the SATCON. It doesn't provide an intensity estimate that the other 3 techniques do. A weighting scheme utilizes each method's bias and RMS values for different scene types for the ADT, and also instrument scan angle geometries for the microwave sounders. So all of these different elements are placed into the regression equations for the different elements, and it is used to derive the SATCON estimate. Here are some validation statistics for the SATCON. The top shows an independent sample from 2015 to 2019 for the North Atlantic and East Pacific against ground truth aided best track measurements, while the bottom is a WestPac sample derived during 2 field experiments in 2008 and 2010 using aircraft reconnaissance measurements directly. SATCON was superior to both the individual SATCON members as well as the estimates provided using a simple average of the methods instead of the weighted average in the top sample, showing the value of the member weights. The bottom shows the SATCON versus the ADT and manual Dvorak estimates obtained during the field experiment from forecasters on station during the experiment. So where can you get the SATCON estimates? Well, again, it's on our Tropical Cyclone webpage. You can go directly there using the link provided at the top of this slide. And there you will see the various SATCON estimates, some graphical displays in Vmax or pressure, and you will also see the various member estimates provided on this page also. Here is a SATCON example for Typhoon Mitag in 2019, showing the SATCON in red, along with the various SATCON members using the various symbols, and the JTWC best track in black. In the orange box, it should be noted the large deviation by the various members of the SATCON, and you can see there's about a 40-knot spread in the estimate intensities. The SATCON weights in the example here weighted the two ATMS estimates much higher than the ADT, since the ADT at this time was noting a CDO scene type where the ADT tends to plateau and underestimate the intensity of the storm. Here is that same example in terms of mean sea level pressure. Again, you see many of the same parameters plotted for this estimate. Okay, and this one there, so there was an observation as the storm made landfall, and you can see the 964 pressure observed was in good agreement with the SATCON estimate. Here's another case of Hurricane Maria in 2017. This was a very good case to look at just because it showed a very good case of rapid intensification, shown here in the yellow circle, and how well the SATCON and ADT for that were able to adjust over this rapid intensification period. One thing also to notice, you will see some fluctuations in the SATCON that you don't see in things like the best track, and those are due to diurnal fluctuations or eye wall replacement cycles. These are shown in the SATCON and smoothed out in the best track estimates. So that is another positive aspect of the SATCON, as you can get some of these smaller fluctuations that the best track tends to gloss over. Here's another example, this one for Tropical Cyclone Gaja in 2018. This example highlights the differences between the best track in black and the SATCON. It should be noted that the SATCON was validated at landfall when a direct observation of the storm intensity was made. You can see the observation of 962 with a wind estimate of about 90 knots was much closer to the SATCON and ADT estimates than the official best track estimate. Finally, this is one case just showing again the eye wall replacement cycles that are able to be captured with the SATCON and how they can vary over time, whereas the best track tends to smear them out and not capture those eye wall replacement cycles. So what's next for the SATCON? Well, the new possible member for the SATCON include the AMSU-like sounders from the upcoming Tropics CubeSat constellation. These small sats will provide a much higher spatial and temporal resolution analysis than the current satellites available now, like the ATMS and SSMIS, some of which are getting quite old and past their expected lifetimes. Some other future additions to the SATCON could include two machine learning methods developed at CIMSS. The first is a deep micronet model developed by Tony Wimmers, which provide probabilistic intensity estimates using microwave imagery. The second is a new experimental method, the AIDT, just developed to augment the ADT, which I will talk about in the next portion of my talk. Finally, here is the SATCON reference that was published in 2020. In weather and forecasting, so you can take a look at that and gather more information about the SATCON. And the final portion of my presentation today will focus on this advanced Dvorak technique enhancement called the AIDT. Again, this is developed by myself, Tony Wimmers, and Chris Veldon in the last year, and it is experimental right now, but we are presenting it here because it shows great promise. So why do this machine learning methodology? Most current methods focus on direct examination of satellite imagery, whether it is geostationary or polar orbiting. The deep micronet that I just mentioned previously is one example. These models can take a great deal of time to develop because of the large amount of data being examined. But the ADT already interrogates the imagery and provides analysis parameters that we can look at with itself without having to look at the actual imagery, so this can save quite a bit of time in these machine learning techniques development. Here are some of the parameters that are being used within the AIDT in order to derive the maximum sustained wind estimates provided by the algorithm or model. Some of these values are scene type dependent, while others are variables used in the regression equations that I covered previously. So we examined various ADT output history file parameters from all global storms from 2005 to 2018 at a 30-minute resolution. These values are called features in machine learning analysis, and the final best track maximum wind speed estimates were utilized as a ground truth. These are also called label data in the machine learning world. The final model derived was developed using the global data set, but it was applied to the storms in the 5 primary tropical cyclone basins: the North Atlantic, the East and Central Pacific, the Western Pacific, North Pacific, the Northern Indian Ocean, and the South Pacific and Indian Ocean regions. Okay, so data from 2005 to 2016, minus 3 years, which I'll explain in a minute, were used to train the model. Okay, once the model is derived, it is validated using the 3 removed years. This allows us to validate and tune and optimize the model using various adjustments to the model. The tuning and optimization process can take a while to do, since it can require many manual adjustments to the parameters, like the number of levels or the number of nodes in the model. And I'll go into this a little bit, but I don't want to go into a lot of it because that can take up a lot of time. Once the model is correctly tuned and optimized, the models was independently tested using data from 2017 and 2018. The total number of ADT records using the various data sets numbered over 225,000 individual records. So we had a very large data set to look at, which is a good thing. Okay, the final model, again, was a fully connected deep neural net using a regression-based loss function. It only had one hidden layer of 32 neurons and one final output layer containing the intensity estimate. Models with more layers and/or neurons tended to overfit the model toward the training data and increase the errors obtained when we used the validation data to look at and analyze the model that was being developed. We also tried many other analysis methods, but this one proved to be the best. That is a regression-based network. A final 3-hour time averaging scheme was also applied to help smooth out some of the noise that was obtained from the initial model. And it helped to reduce the error by about 1/3 of a knot. So here is a schematic of the model. Again, there's just one layer of 32 neurons. We have 26 values or features going into those neurons and one output neuron with the intensity estimate coming out. The table here contains the error analysis of the AIDT model using the 2017 independent test data set. The model was applied to the 5 individual ocean basins as well as the entire combined global data set, which is shown in the yellow in the bottom right corner. AIDT-R is the unaveraged data set, while AIDT is using the 3-hour time-weighted average. The original ADT estimates are also shown and can be seen that the improvement of about 3 knots in RMSE was obtained by the AIDT model in the global data set over the ADT estimate itself. This is a significant improvement to the ADT, one that it would have taken many years of research to achieve using more manually extensive techniques of research. Here are some examples for the Atlantic Basin using the 2017 independent data set. The highlighted regions note the areas of greatest AIDT impact, mostly the intensities where the ADT has struggled in the past mainly the tropical storm and weaker hurricane and typhoon intensity ranges. The ADT is in blue, the AIDT is in red, and the NHC best track is in black. The highlighted regions demonstrate the impact of the AIDT during the formation and dissipation stages of the storm, where the AIDT can struggle at times, typically when using the curve band and shear scene types that I mentioned previously. These scene types have not been studied much and still rely on the original Dvorak methods. Thus, the use of the machine learning techniques in the AIDT has saved us potentially a significant amount of research efforts, which is very exciting. Here are 4 cases from the East Pacific during 2017. Many of the same intensity range improvements are highlighted as with the Atlantic cases I just showed on the previous slide. However, one case, Dora in the upper left corner, does show the adjustments made by the ADT during a Category 2 hurricane. Here are some cases in the West-North Pacific. Again, many of the same areas of impact are noted, but also, like in the case with Von and storm number 25, you can see some modification in the very intense period, like around 140 knots, where you can see the AIDT modify the ADT estimates fairly significantly in both directions, over and under the ADT estimates, which is a very good thing to see. But like in Storm 7 in the upper left, you can see there was very little advancement or modification. In order to emphasize the impacts of the AIDT on the ADT, we examine the statistical improvements obtained during the 4 main scene types utilized by the ADT. Again, we're using the 2017 independent data set, using the global entire data set. As I highlighted before, the most impact was shown in the shear and curve band scene types. Again, these scene types have not been researched as much as the other 2, the I and the CDO scene types, which used new regression techniques. So these improvements have saved us a lot of time and effort, which is, again, a wonderful thing to see. Another way of emphasizing the impact of the AIDT on the ADT estimates during certain phases of the tropical life cycle, we break down the statistics by hurricane and typhoon intensity categories. Again, noted previously, we are seeing the largest improvements in the tropical storm and weaker hurricane or typhoon intensity ranges. These are again where the ADT is typically using the curve band and shear scene types, but also the CDO scene type is being used quite a bit in the Category 1 and 2 classification bins. So again, we are the most impact of up to or over 4.5 knots of improvement are being seen in some of these categories, which is again a significant improvement over what we are obtaining previously. Finally, this graph shows a comparison of the AIDT errors to other machine learning and statistical methods available right now. And you can see the AIDT errors are very competitive to, or in many cases better than, some of the cutting edge techniques being developed now. While these are not homogeneous comparisons, they represent a good comparison of performance among the different techniques. Highlighted here are the AIDT, the ADT, and the SATCON presented earlier, as well as other methods such as the deep micronet reference previously developed by Tony Wimmers, which uses microwave imagery instead of IR. The Lee 2D3 method should also be noted, since it is probably one of the better direct image analysis deep learning methods out there right now that uses convolutional neural networks to directly analyze the IR imagery as shown in this graph. We actually started our initial study trying to mimic or look at a similar test case with this, but decided to not try to duplicate what Lee has already done, and instead that's why we went with the direct analysis of the ADT parameters informing the AIDT model. So again, looking at some of these statistical comparisons, you can see how well the AIDT performs in direct comparison to these other methods. So in conclusion, again, we hope that the AIDT article will be published later this year once it is through the review process, and we will include the AIDT within SATCON to further improve the SATCON performance. Finally, to wrap things up, if you want to obtain any of these intensity estimates in real time, they are available on our Tropical Cyclone webpage, located at the address at the top. The ADT and SATCON are available in real time for all current global tropical cyclones. The AIDT is not currently available, but will be once our paper is accepted and published. We also have many other products available on our TC webpage, including atmospheric motion vectors, shear and vorticity and other derived products, Archer storm position estimates. I mentioned the Archer previously, so if you want to get a closer look at that, you can. We also have Mimic TPW products and a tropical cyclone diurnal cycle product being shown on our webpage. I thank you very much for your time and your attention, and if you have any questions, I'd be more than happy to answer them now. Thank you very much. I know in some of these conferences with a lot of people in a room like that, if you want to ask a question, I think there are ways to like type it in if that's a better option if you have some questions. I don't know if that's an option for everybody there, but it might be a better way because sometimes in those large halls it can be hard to understand things, but I just want to put that out there.
Or we also have a bunch of the audience coming from Taiwan Central Weather Bureau. 气象局的同仁哈，如果 if you have question, you also can type or ask online.
Yeah, I know it was a very specific talk about certain specific products. So I know some people might not be interested in tropical cyclones, but if you are, I can stick around for a while afterward. If some people want to ask questions and don't want to stick around for the question and answer session, I can definitely just stick around for a while afterwards.
Okay. Actually, I got two. Actually,
okay.
they got kind of users. A user also have a bunch of so-called typhoon fans on internet. They're using ADT algorithm and the T number quite often. They share. They even make the very fancy kind of picture share on Facebook or their Twitter. That's what I see. And they are very young, about age of 20, 25. They are typhoon fans, local student kind of club. All right, so I got two. One will become your slide 25. It's about the SATCON. And you say you relocate the warmest spot from microwave sensor and then to point position at the same location. So I think that's based on, because the typhoon is barotropic, so it's a vertical extended. So what if the eye is tilt from the kind of warm center is not exactly at the typhoon center? Does that still work? Does this still work?
Does the SATCON still work if the center, the warm core center is not over the storm center? Is that what you're asking?
Yeah, exactly.
Okay, yeah, it will still work. The algorithm will search for a large region for that warm core structure, and then it will adjust the algorithm over towards that warm core center and center it upon that warm core center and then do its analysis. So the storm does not have to be, the warm core structure does not have to be right over the storm center. And sometimes you will get that in highly sheared storms or storms that have a tilted kind of a storm center. So especially in weaker stages of the storm. Usually when you have an eye of the storm is very apparent, usually the warm core is centered pretty much right over the eye of the storm. Did that answer your question?
Yeah. You answered my question. And also, I also congratulate to your kind of third part, AIDT. That's quite
Yes.
promising. That's quite promising because a new method introduced to improve the current product. So I also curious about the largest improvement in TS and H1 category. Uh, yeah, I'm just wondering, curious about, is there any primary reason? Is that due to more obvious in some microwave data, so that have big improvement in these two categories, or other possible reasons?
So you're asking about the ADT and if we've used microwave in it? Is that what you're asking?
Actually, I'm asking, there are two categories. You mentioned the largest input by using AIDT, which is TX and
Oh, yes.
H1 category. I'm not sure is what's the primary reason. I'm just guessing, is that due to in microwave sensor more sensitive in that at that time due to the warm core.
Yeah, that's a really good question, and it's something that we're still looking at. But primarily, the use of the microwave data is a big improvement, with it. But with the ADT, we don't use the actual imagery. We use it as kind of a proxy to reclassify the storm at a couple different intensity ranges, because it's very difficult with microwave imagery to grasp a very solid estimate of tropical cyclone intensity. So what we believe the largest impact is with the microwave data, because of that central dense overcast structure. That's very difficult in the IR imagery to decipher. That's been a problem with the ADT and the underlying Dvorak technique, that it's very difficult in that situation to just gather any usable information from the satellite image in that case. What we think is happening is that the machine learning is actually deciphering information that we are not seeing or we hadn't explored fully in our initial analysis and some of our regression equations and that. So we believe that because we are using the machine learning, it is finding the new information within that data that we're using and improving the estimates in that CDO case. And that's when typically the CDO is when you have a tropical storm or weaker hurricane or typhoon category. So that's what we think is happening. And that's a tremendous improvement for the ADT and the Dvorak, because like I said, it's been a troublesome region for us to try to decipher. And using the microwave image that we do use within the ADT only provides a little bit of information, but because we did apply the machine learning, we do think that it's finding more information than we thought was available previously. So that's the excitement, as all of the people there who probably are getting into machine learning and neural network. It is a great way to find and do some data mining and find information that you didn't know was previously available in a data set. So that's the exciting part for us, is that it's speeding up our research quite a bit. But now we have to go back and try to figure out exactly what it's grabbing onto when it's doing those improvements. So I hope that wasn't too long of an answer, but that's basically what's going on, that we think is going on in that region.
Well, thanks. Yeah, that explains some part of my question.
Okay.
Yeah.
Sorry if I didn't answer it all. I apologize.
No, great, because everyone doing the research, that's we have to make the assumption and guess and to prove it.
Right, and a lot of the routines that actually look at the satellite imagery, like I mentioned, some others, they can actually look at the satellite image, but they're not going to grasp a lot more information than we do, just because we're just using variables that go in and values instead of actually looking at the satellite imagery. But if you get combining those satellite images is what a lot of studies are doing and looking at. And that can be very difficult to analyze also because there's just so much data to look at. So why we did the study was just try to do a simple, let's just look at some data values that we already have and see if we can get some improvement out of the ADT. But some of those studies that I also mentioned, they just look at the satellite imagery, and you can see that they did gather some information and make improvements to, the Dvorak and all that, but it's still not, there's still so much information to grasp looking at images that it's a very difficult problem to solve. So anyways, if there's any more questions.
I see one.
Okay, so 51, the slide shows many techniques. Some techniques are used. Okay, some techniques use other channeled observation. I was confused at why the AIDT doesn't use water vapor channels or other channels from LEO or GEO in the ADT. Is there improvement to these channels? Contributions weak? That's an excellent question. So basically what they're asking is, why don't we use other channels in our technique? And that goes back to the ADT and how it runs. It only utilizes IR data. And so we just examine that. We do input some microwave information, but it's a very limited amount. So that's why we don't use other channels. Now, that being said, you have just touched upon what we're going into next with our next amount of research, that we're looking at water vapor and a water vapor IR differencing that I had published a paper back about, 10 years ago on an IR water vapor differencing technique that showed a lot of promise for looking at intensity of tropical cyclones. So that is something we are actually looking at. So you did touch upon some of the research that we're getting into right now. Why we don't use more LEO is that has to do with basically there's not a lot of good channels available because there's very limited amount of microwave data available because the satellites that are up there are getting close to the end of their life cycles and are breaking and aren't being replaced fast enough. Now we do have that that one constellation, the Tropic constellation, that's being added, and that will be a tremendous boon, and it will give us a lot more information to now add into something like the AIDT. But the AIDT was basically just a quick study that we did, just using the information that we have derived from the ADT to see if we could grasp and get any more information out of the data that we already have that we hadn't explored. That was the idea. Just a very simple experiment that we wanted to try that was something different than some of the other experiments that other people have tried, like I showed on that slide 51, where other people have used satellite imagery directly. So I hope that answers the question that you had.
You've got that one from local audience.
Thank you for your presentation.
Sure.
Now, in the AIDT model, which input variable is most important?
Which of the elements is most important? That's a very good question, and we did some feature analysis techniques on that. We didn't publish them in our paper because the findings were, they weren't real firm on which parameter was the best. When we looked at it, obviously the best parameters when we did some initial studies were the CI numbers, obviously, and all those raw T numbers and those various numbers were very important, obviously, but also the eye temperature, the microwave score value that went into it, and some of the other ones that were interesting were like the longitude was an interesting value. So those were some of the more important features that went into the ADT. But when we did some of that analysis, it was unconclusive as to which one was the most important because but some were obviously a lot more important than others. But they were all important. That was the one thing that was interesting, is that if we took some out, the accuracy of the algorithm did reduce. So that's why we left them all in there. Okay, if anybody has any questions, if they want to ask me any questions in an email afterwards, if you have, if you wish to do that, feel free to send me an email. I believe the organizer has that, and they can pass that along if you're very interested. Please feel free to, even about the StatCon, I can always answer your question or pass that along to Derek Herndon or Chris Veldman, who are the organizers. Or if you have any other questions about any of our other products that I mentioned on my last slide, if you happen to look at our Tropical Cyclone webpage, we're more than happy to answer any question that you may have about any of our products.
Tim, congratulations and thanks. Hopefully you and your family are very well during the pandemic.
Yes, we are. We've been very healthy. We've been very fortunate, and all the best to everybody there. Thank you so much again for your attention and your time, and for inviting me to present.
Okay, thanks for your sharing. Appreciate it.
Okay. Take care. Bye-bye.
Okay, bye.